All right, now let's do some electrostatics homework that involves electric potential energy and electric potential. Now, I know this is confusing. Just remember, if you have a charge moving in a uniform field, a distance d, it'll have a change in potential energy that's equal to minus QED. Keep your signs. All right. And the electric potential is defined to be the change in potential energy divided by charge. So we can also write this as the change in potential energy is Q change in V, where the electric potential is ED. It's the change in potential a charged particle undergoes is going to be equal to the electric field, the magnitude of the electric field, times how far they move in that field. So these words are close, I know. A uniform electric field of magnitude 250 newtons per coulomb. Okay, electric field. I know that's E. A 12 microcoulomb charge, this is Q, moves a distance, D, in the field. What's a change in electric potential energy? Ugh, let's write everything out. The electric field is 250 newtons per coulomb. Charge is 12 times 10 to the negative 6 coulombs, and the distance it travels is 0.2 meters in the direction of the electric field. So the electric field goes this way, and then the particle is going to move a distance d in that field. We're looking for the change in potential energy. Well, the change in potential energy, and I know I want the energy because I see that word right there, energy, is minus Q E D. Now D is in the same direction as the field, so D is positive. So the change in potential is minus, keep your minus signs, Q, which is 12 times 10 to the negative 6. E is 250 newtons per coulomb, and the distance is 0.2 meters. Now, there are no negatives in here, so we're going to keep the negative sign. 12 times 10 to the negative 6 times 250 times 0.2 is 6 times 10 to the negative 4 joules. Now, what's a change in electric potential energy? So again, we're looking for change in PE. A lightning bolt if 35 coulombs of charge. So what is this? What do you think this is? Yep, it's going to be Q. Travels to the ground from a cloud 2,000 meters above the ground. This has got to be D. In the direction of the field. Assume the electric field is uniform and has a magnitude of, okay, so here's my electric field, E. So basically what we have is we have an electric field going this way. And the charges are also moving this direction. So I have Q is 35 coulombs and D is 2,000 meters. And the electric field is 1 times 10 to the 6 newtons per coulomb. Now, the change in potential energy, electric is minus Q E D. So it's minus 35 coulombs. E is 1.0 times 10 to the 6 newtons per coulomb, and the distance it's traveled is 2,000 meters. So I get negative 7 times 10 to the negative 10 joules. Now, what does this really mean? It means that this 35 coulombs of charge literally dropped. It lost energy, and that's okay. Think of a ball dropping. If I drop a ball, its potential energy decreases. A charge moves a distance of 2 centimeters in the direction of a uniform field. So I know D is going to be positive 2 centimeters. Now I'm going to go and convert this to 0.02 meters. Um, in the direction of a uniform electric field that has a magnitude of 215 newtons per coulomb. So that's E, with 215 newtons per coulomb. The change in electric potential energy is negative 6.9 times 10 to the negative 19. So the change in potential energy electric is negative 6.9 times 10 to the negative 19 joules. Find the magnitude of the charge. So we're looking for Q. Well, I know the change in potential energy is minus Q E D. To solve for Q, I divide by ED, and I'm going to have a negative as well, so I'm going to divide through by negative ED. So Q is negative change in potential energy divided by ED. Remember, it doesn't matter whether this negative is in the numerator or denominator. So this is negative. Let's see. The change in potential energy is negative 6.9 times 10 to the negative 19. E is 215. And D is 0.02. Now, this negative is going to cancel this negative, so it's going to become positive. Multiply across your numerator. And so negative 1 times negative 1 is positive, and this is going to be 6.9 times 10 to the negative 19. Now I want you to go ahead and multiply your denominator out. So it's 215 times 0.02 is 4.3. So 6.9 times 10 to the negative 19 divided by 4.3 is 1.605 times 10 to the negative 19 coulombs. Now, for these problems, I've gone on and put the formula chart here. I have 120 joules of work are done to move 1 coulomb of charge from a positive plate to a negative. What voltage exists between the plates? All right, so I'm just going to move this down here. Sometimes it helps to have the formulas there for you. All right, I have 120 joules of work. So the work is equal to the change in potential energy here, and that is 120 joules. To move 1 coulomb of charge, that is my Q. Q is 1 coulomb from a positive plate to a negative plate. What voltage exists between the two plates? Um, so I know the potential difference is equal to the change in potential energy divided by the charge. So the change in potential energy is 120 joules divided by 1 coulomb of charge, or 120 volts. Now, again, I'm showing you the formula chart because these do get a little confusing. A voltmeter reads 500 volts. Obviously, that's V. When placed across two charged parallel plates, the plates are 0.02 meters apart, so D is 0.020 meters. What's the electric field? We're looking for E. Well, I know V, and you can use delta V or V. Physicists get lazy and we just drop the delta. V is ED, so E is V divided by D. So this is 500 divided by 0.02, or 2.5 times 10 to the fourth newtons per coulomb. If the uniform field exists between two parallel plates is 1050 newtons per coulomb and the potential difference is 100, how far apart are the plates? Well, this is my electric field and this is my voltage. So E is 1050 newtons per coulomb. V is 100 volts. So let's see, what formula are we looking for? V equals ED. We're looking for D, so I'm going to divide both sides through by D. Oh, no, I'm looking for D. Sorry. Again, it's early in the morning. I'm looking for D. Always circle what you're looking for. So I've got to divide through by E. So the distance between the plates is the potential difference divided by the electric field between them. So this is 100 volts divided by 1050 newtons per coulomb, or 0.095 meters. Now, if a 0.02 coulomb particle experiences 40 newtons of force due to the electric field, what's the strength of the electric field? All right, coulombs. That's going to be my charge, and this is my force. So Q is 0.02 coulombs. F is 40 newtons. And I'm looking for E. Now I'm looking for the relationship between F, Q, and E, and I know that F is equal to QE. So to solve for E, I divide both sides through by Q. So the electric field is F divided by Q. So this is 40 divided by 0.02, or 2,000 newtons per coulomb. Now, if the electric field in the atmosphere is about 150 newtons per coulomb downward, what's the direction of the electric force on a positively charged particle? Remember, the electric field, it's pointing down. That's E, okay? It will push a positive particle in this direction. So the direction of the force on the positive particle has got to be downward. Or you can say in the same direction. Find the electric force on a proton with charge 1.6 times 10 to the negative 19 coulombs. All right, so E is 150 newtons per coulomb, and the charge on a proton is 1.6 times 10 to the negative 19 coulombs. F is QE. So this is 1.6 times 10 to the negative 19 coulombs times an electric field of 150 newtons per coulomb, and I get 2.4 times 10 to the negative 19 newtons. Ah, that's wrong. That should be newtons.